In every version and proof of the central limit theorem that we've seen so far, independence played a central role. In the characteristic function methods, independence gave rise to the factorization property, which made the proof work. In our Stein's method approach from the previous lecture, a key step was to remove one term at a time from the sum, and then use the fact that that term is independent from the rest of the sum with that term removed. However, out there in the wild, independence is often hard to find. And so we'd like to have an approach that would work where at least we have some mild dependencies. Let's explore the idea of local dependencies. To get started, here's an example. Suppose we have a sequence of IID random vectors in RD, and for convenience, let's center all of the entries. Then we can take those random vectors and spread out their entries. That is, the first vector with D entries can be listed x11, x12, up to x1d, and then take the next vector, x21, x22, up to x2d, and so on down the line, producing a sequence of random variables that are not independent from each other. They do, however, have neighborhoods that are independent from each other. The first D are independent from the next D and all of the other groups of D, while within each group of D, there are dependencies. Now, this example has a lot of structure, and in fact, we'll be able to put it in a form where the classical central limit theorem will apply, because we can write the sum of the first n times d terms as a sum of n random variables, y1 through yn, where yj is the sum of the entries of the jth random vector. Now, because these neighborhoods of size d are independent, we see that the yj are independent by the grouping lemma, and they are also identically distributed because the distribution of yj is determined by the joint distribution of the entries of the jth random vector. It's just a fixed function, the sum of those entries. But those random vectors are identically distributed. They all have the same joint law. And so if I take the fixed function, sum, of the joint law entries, I'll produce the same distribution for each of the yj's. So we're set up for the classical central limit theorem, at least for this sum. The random variables yj are centered because of our assumption on the entries of the xj's, and the common variance, which is just the same thing as the second moment of y1, is going to be the expected Euclidean length of the vector, say, x1. And so if I take s and d divided by root nd, well, we can just write that as 1 over root d times the sum of the first n y's divided by root n. And by the classic central limit theorem, this is going to converge in distribution to a normal with variance given by this common variance here. Now, the addition of this 1 over root d term here means we have to scale that down, and so this will converge in distribution to a centered normal of variance sigma squared over d. Now, that's only a subsequence that we want to consider. We'd like to consider Sm over root m for every m, not just those m that are divisible by d. But it's easy to see that if I take Snd plus k divided by root nd plus k, and look at the difference between that and Snd over root nd, where k is some number between 0 and d, where d is fixed, then this is going to converge in probability to 0, and so we will indeed get that the full sum, standardized, converges to a rescaled normal. That approach took full advantage of all of the structure that we had here. We wouldn't be able to handle the same situation if the neighborhoods had varying sizes, at least if they were growing. And it could be worse. For example, consider the following. Suppose I start with an IID sequence of random variables, x0, x1, x2, etc., the kind for which the classical central limit theorem applies, but then I take a new sequence, yn, which I get by multiplying each term in the x sequence by its preceding term. Yn is xn times xn minus 1. Now we only have local dependencies. We see from here that yn and ym are independent so long as n and m are at least 2 units apart. However, each yn is dependent on both of its neighbors in the sequence, so the dependency neighborhoods always overlap, and an approach like this is just not going to work. So how can we handle overlapping dependency neighborhoods? Well, for starters, instead of talking about neighborhoods, let's talk about a graph structure that we have here. If I have a collection of random variables indexed by some set v, in the previous examples v would just be the set from 1 up to n, the dependency graph of that set of random variables is the graph, meaning that we put a collection of edges between the vertices v, the index set, where we put an edge between two indices I and j if and only if xi and xj are not independent. Just by convention, all graphs that we'll deal with are loop-free, so that means we aren't actually putting an edge between I and I, even though xi and xi are usually not independent from each other. So, for example, that means that if the index set were the natural numbers or some finite subset thereof, and we actually had independent random variables, then the dependency graph is trivial. There are no edges. Now let's look at the example that we just worked out, where we start with IID random vectors and then spread out their entries to form this sequence with d-dependent neighborhoods. Well, in that case, I don't know exactly what the graph structure is, but I know that wherever there are dependencies, they're only within the d neighborhoods. Now, whatever the graph structure is in the first d neighborhood gets copied over to all of the others because of the identical distribution. But in this case, the key feature is that the graph is segregated. It's really just a disjoint union of d vertex graphs, all of which are isomorphic. And it's that structure that allowed us to easily morph this example into a classical central limit theorem approach. Now let's look at that other example that we don't know how to handle yet. Suppose that we start with IID random variables and then take the successive product of a term and its previous term. Well, now the dependency graph looks like this. Each term is not independent from its two neighbors, but there are no edges further away. So that's a pretty simple graph, but it doesn't have the same kind of segregated structure that this graph did, which is why we don't know how to handle it in the same way. What is it about this graph that makes it simple? Well, let's talk about the degree of a graph. In any graph, each vertex has a degree, which just means the number of edges that come out of that vertex. So here, each vertex has degree 2, except for the endpoints, which each have degree 1. For any finite graph, we say that the degree of the graph is the maximal degree of any vertex. So this graph here has degree equal to 2. This graph here, I don't know exactly what the degree is because it depends on what edges there are actually in each of these, but the maximum degree of this graph is d minus 1 because each vertex here has a maximum of the other d minus 1 entries of its neighborhood that it could connect to. In both of these cases, a critical observation is that if we take a sequence of these graphs, that is, if our vertex set is the index set from 1 up to n, and we have a graph for each n, the degree is not growing with n. And it turns out that that is all that is needed to get a central limit theorem. In fact, given the right setup, a central limit theorem can hold even if the degree grows slowly enough with n. To start considering the ideas of how that might work, let's look at the variance of the sum of the terms corresponding to such a graph. Suppose that I have a collection of random variables, xj, for j in the index set v, which will be the vertices of its dependency graph. And of course, they should all be L2 if we're going to talk about variances. If we're going to talk about a central limit theorem, we're going to take the sum of those random variables, and the first thing we're going to need to do is calculate the variance of that sum. If the x's are independent, then it's just the sum of the variances of all of the terms. How bad can it be if the dependency graph is not trivial? Well, the answer is that the variance is bounded by this, the sum of 1 plus the degree of each vertex times the variance of the term at that vertex. If the graph is trivial, that means that all these degrees are 0, and we recover the usual variance of the sum of the variances formula. And I'll just point out that this is obviously bounded by 1 plus the degree of the whole graph times the sum of the variances of all of the terms. So if the dependency graph for the first n terms in a sequence of random variables has degree that doesn't grow with n, that means that the variance of the sum of the first n terms is just going to be bounded by a fixed constant times the usual sum of the variances, and that's very helpful. Let's see why this is true. The variance of the sum is the expected value of the square of the sum of the centered random variables, and as usual, we'll expand that as the sum of all of the covariances, like this. Now let's separate out the terms where the two indices are the same, giving us our sum of the variances of the individual terms. That's what's going to give us this term 1 here, plus the sum over all of those terms where I and j are not equal. And we'll write that as the sum over I and then the sum over j not equal to I of this term here. Now we use the dependency graph structure. If I have a pair of indices I and j that do not form an edge, well, that means that xi and xj are independent by the definition of the dependency graph. And of course, it therefore follows that xi and xj centered are independent. And therefore, because these are L2 and therefore L1 random variables, the expected value of the product is the product of the expected values. But those are centered, and so that's just 0. And so what that means is that this sum here is really just a sum over all of those indices j that have an edge connecting them to the index I, which is what this notation here means. J is similar or equivalent to I. In this case, just means that ij is an edge in the graph. Now we're supposed to get a bound in terms of variances of individual terms, but we still have here an expected value of a product of different terms. But for that, we can just use the arithmetic geometric mean inequality. In other words, just the fact that for any two real numbers, a and b, the product a times b is less than or equal to 1/2 the sum of the squares of a and b. And so this is less than or equal to 1/2 the sum of the variance of I and the variance of j. So far we have that the variance of the sum is the sum of the variances plus this term here. And let's separate that out into the two parts. It's the sum of the variance of I plus the sum of the variance of j. Now for that first term, this doesn't depend on j, and so we can pull the variance of I outside that sum, and what we just get is the sum of the variance of xi times the sum over all those indices j that have an edge to I of 1. Well, that just means that we're counting the number of edges that come out of index I, which is exactly the definition of the degree of I. So that first term gives us 1/2 the sum of degree of I times the variance of xi. The second one seems like it'll be a little more complicated because here we're summing the variance of xj inside this sum over j. So let's just think for a moment about what this means. At the end of the day, we're going to get a sum of variances of terms. And the question is, what will be the scalar multiples inside here? How many times will we count each variance term inside this sum? Well, what we're doing is, for a fixed I, we're including the variance of xj for each j that is connected to I. Let's think instead about a fixed j. How many times is variance of xj going to get hit in that sum? So suppose that this is our index j in the graph here. Well, as I move around through the whole graph, it's going to get hit each time I start with an I that is connected to it. And so I'm going to get one copy of each of those terms for each I that is connected to j. And what that means is exactly that what gets put here is the degree of the vertex j. There's a symmetry between these two terms. And just to double check that we're not making a silly mistake, let's look at this example here. Let's do this sum for this graph. By the way the sum is written, that means that we need to start with each vertex, say this one, and include each term that is connected to it. So we'll have this one and that one, as we're summing starting with that term. Then as we move to this term I, that means we're going to include that one and that one again. And then as we move to this one, it's connected to this one, and that one. Now we have starting here, that means we include this term and this term. And finally, this one is only connected there. And what we see is that the number of circles that I've drawn around each vertex is exactly its degree. So that says that this term here is 1/2 this plus itself, again, which exactly gives us this, and we add in that term, which gives us the result. Okay, so that just tells us how to calculate, or at least estimate, variances. So how are we going to get normal concentration out of this? Well, the Stein method approach allowed us to make calculations by taking one term out at a time and having it independent from the others. In this case, where we have a dependency graph, what we'll have to do is take each term and remove from consideration everything that's connected to it in the dependency graph. And what's left when you remove those terms, the rest of the graph is independent from that. Now, we won't have a uniform structure as we do that unless we have a simple example like the first one that we considered today, but we will still be able to follow through with the same argument that we gave using Stein's method to prove the central limit theorem. And so let me state the result here. The theorem is as follows. If I have a collection of random variables indexed by a vertex set, V, and let's assume that they're L4 in order to make this proof work, we'll center them, and let G be their dependency graph, which is an edge set on this vertex set V, placing an edge anytime that two random variables, xi and xj, are not independent. Let sigma squared be the variance of the sum of those terms, which we just showed is bounded by this quantity here. And if we take the standardized sum of those random variables and compare it in Wasserstein distance to a standard normal, then we can use Stein's method to prove the following bound. The Wasserstein distance between W and a standard normal is bounded by a sum of two terms. This one involves a normalized sum of the fourth moments. This one, a normalized sum of the third moments. And what's critical about this is that we have 1 over sigma squared or sigma cubed in the denominator of these two terms, and the key bounding constant in both cases involves the degree of the dependency graph. Now, I am not going to go through a proof of this. It is philosophically very similar to the proof that we gave of the central limit theorem using Stein's method in the previous lecture, just quite a bit more fiddly. If you'd like to see the details, I recommend that you see the nice survey paper of Nathan Ross, which I've linked on the course webpage, that lays out approximately 3 pages of calculations to show a version of this bound. Now let's see how we can use it. Let's take the example from the first slide that we didn't know how to handle. Suppose they start with a sequence of IID variables. Let's make them all L4 so we can use these bounds and standardized. And then let's take yj to be xj times xj minus 1 so that the dependency graph looks like this. As we saw, that means that the degree of the dependency graph is 2. And so in this bound, we're going to get just constants here. Of course, we need to see that the xj's satisfy the conditions of the bound. Well, let's just note that the expected value of yj to the kth power is the same thing as the expected value of xj minus 1 to the kth power times xj to the kth power, and xj minus 1 and xj are independent. So that's just the expected value of xj minus 1 to the k times xj to the k, provided that these terms are both in L1, which by our assumption of the x's being L4 will be true if k is less than or equal to 4. And by the identical distribution of the xj's, this is just the expected value of x1 to the kth power squared. So that's certainly finite for k less than or equal to 4, and that means that the yj's are also in L4. Now notice that just like in the first random vector spread out example, if I take xj minus 1 and xj as a random vector, its joint distribution is the same as the vector xj plus 1. That distribution is just the product of the law of x1 with itself, no matter where we are in the sequence. And so just like in that first example, we therefore have that the yj's are identically distributed. Yj is just a function of xj minus 1 and xj, that fixed function being the product function in this case. And so since it's a fixed function of this fixed distribution, that means that they all have the same distribution. They are not, of course, independent, but they are at least identically distributed. Now, in order to apply this bound, we're going to need to compute, or at least estimate, this sigma. We have a bound for it from the previous lemma in terms of this degree here, but we actually would like to know exactly what it is, and that's not hard in this example. Let's compute the covariance of yi and yj, if I and j are different. Because the y's are centered, given that the moments of y are the squares of the moments of x, the covariance is just the expected value of the product. And if we write out what that is, it's the expected value of xi minus 1, xi, xj minus 1, xj. Let's decide that we'll write I less than j here without loss of generality. And now, in order to consider this sum, notice that with this assumption in place, what that means is that, well, I minus 1 is certainly less than I, and I is less than or equal to j minus 1, since I is less than j. That's certainly less than j. Now, depending on how I and j sit relative to each other, we could have I equal to j minus 1, but no matter what, these four numbers, I minus 1, I, j minus 1, and j, contain at least three distinct numbers. In other words, this is always equal to the expected value of xi minus 1 times the expected value of xi times xj minus 1 times the expected value of xj, because all of those variables in question here, this one, and this one here, are in L1, since these two are in L4, and this product of two L4 random variables is in L2. But these are centered, and so no matter what happens to that middle term, this is equal to 0. And so what we see is that although the y's are definitely not independent, they are uncorrelated. And of course, the variance of a sum of uncorrelated random variables is the sum of the variances. But the variance of yj, which is the second moment of yj since it's centered, is the square of the second moment of xj, and xj was standardized to have variance 1. And so this just gives us that the variance of the sum is n, just like in the classic case. Therefore, if we take the standardized sum, it's just 1 over root n times the sum of the y's, and the Stein bound that we just stated on the previous slide gives us the following. We have this with a 1 over sigma squared in the denominator here. Inside we have the degree plus 1 cubed, and this term here. And over here we have 1 over sigma cubed, and the degree plus 1 squared with this sum of third powers there. And now we just note that because the y's are identically distributed, this sum is n times the common fourth moment, which is n times the fourth moment of the original random variable x1 squared. And similarly here, this sum is n times the common third absolute moment, which is n times the third absolute moment of x1 squared. Now this n inside the square root divided by n out here gives a 1 over square root of n. And this n divided by n to the 3 halves also gives a square root of n. And so at the end of the day, what this bound gives us is a certain constant determined by the third and fourth moments of the common distribution of x divided by square root of n. And so we have proved using Stein's method that in this locally dependent example, we still get a central limit theorem. We get that the usual standardized sum converges to a standard normal, and in fact, it converges at the classic rate, 1 over root n. Now that might seem like a contrived example, but as we'll now see, it's closely related to something of great interest in probability and combinatoric circles, and that is Erdos-Renyi random graphs. What is a random graph? Well, this is one model introduced in 1959 of what that should mean, which is heavily studied. We take as our vertex set the indices 1 through n, and we'll fix a probability p between 0 and 1. And what we do is we decide to place an edge between the indices I and j with probability p yes, or with probability 1 minus p no, independently for each pair of indices ij. If we want to be a little more pedantic about that, what that means is that we fix a triangular array of IID random variables, in this case all of them IID, not just along each row of the triangular array. They all are Bernoulli p random variables. And we form the graph, which we call GNP, which is a random graph, to have an edge between I and j if and only if the random variable xij takes the value 1. So for example, suppose that I take my triangular array of Bernoulli random variables and test them in one outcome. I find that these are their values. x12 is 1, x13 is 0, and so on around here. Then I can just read off from there and draw what the graph looks like. There's an edge between 1 and 2. There's no edge between 1 and 3. There's an edge between 1 and 4, and between 1 and 5. There's no edge between 2 and 3 or 2 and 5, but there is an edge between 2 and 4. There are no edges coming out of 3 at all, and there is one edge between 4 and 5. And there is this instance of the Erdos-Renyi random graph. Now notice that I use the convention here when I write a pair ij, I'll always write it in the form I less than j, which means that my triangular array is a lower triangular array. An alternative way to write this would be to make a symmetric matrix by copying these numbers out as the rows as well, and so on. And that's not going to be important to us today. From a naive perspective, all we're really studying are these kinds of triangular arrays of IID Bernoulli random variables, but the kinds of statistics, that is, functions of these that we're interested in, are ones that come from the graph structure. For example, we might like to know how many edges does this random graph have? Well, that's quite easy to write down because an edge is present if and only if the corresponding Bernoulli random variable xij is 1 in value. Otherwise, it's 0, which means that the number of edges is just the sum of all of the xij's. Now, those are independent, identically distributed Bernoullis, which means that this sum, which is a sum of n choose 2 of them, is a binomial distribution with probability p. So we have the full distribution of that random number of edges. So we can see from there that the expected value of the number of edges, which is the expected value of a binomial n choose 2p distribution, is p times n choose 2. We can also quickly reason out what the distribution of the degree random variable is. Let's pick an arbitrary vertex I. What is its degree? Well, the degree of a vertex is the number of edges that come out of that vertex. But that just means that we're taking a sum of 1s over all of those j's that are connected to I. And since xij is equal to 1 if and only if j is connected to I, by definition, this degree will be the sum over all of those j connected to I of xij. By the identical distribution of these, that's not going to depend on which I we choose, and so that in distribution will just be a binomial, this time with parameters n minus 1 and p, because for each fixed I there are n minus 1 choices of j with which it can connect. And so from here we get that the expected value of the degree of any vertex is p times n minus 1. Now that allows us to say some interesting things about scaling limits of these statistics. Typically, one would be interested in the case where as n grows, we allow p to vary with n, usually shrinking. If we let p be fixed, then of course we see in both of these examples the number of edges in the degree will grow without bound. But for the second example here, if we, for example, let pn shrink such that n times pn remains finite, in other words, if pn grows like lambda over n for some positive number lambda, then the degree of each vertex in distribution is going to look like a limit of this distribution, where p grows like lambda over n. And if we apply the law of rare events from lecture 21.2, we'll find that the weak limit of that sequence of probability measures is a Poisson distribution. So that means that the degree of each vertex here converges weakly to a Poisson of rate lambda. There are lots of interesting graph theoretic questions that can be answered by these approaches, but most of the questions that one wants to ask leads to much harder probability problems. And let's look at one such example right now. How many triangles are there in the Erdos-Renyi random graph GNP? What's a triangle? It's just a triple of vertices for which there's an edge between each pair of that triple. In the example from the last slide, there are exactly two triangles in this graph, here and here. No other triple, like these or these, form a triangle because there's at least one edge missing. So in the random graph GNP, a random variable we can study is TNP, the number of triangles. How can we understand its distribution? Well, let's try to write it out again as a function of the generating Bernoulli random variables for the graph. For each triple ijk of distinct indices, which without loss of generality we'll write in the order I less than j less than k, a triangle exists if ij, jk, and ik are all edges. Now what does that mean? That means that xij, xjk, and xik all have to equal 1. And because they're 0, 1 random variables, that's the same as insisting that the product xij times xjk times xik is equal to 1. Otherwise we get a 0. And therefore we see that this random variable is the sum over all triples ijk of this triple product, which looks a lot like the example that we just analyzed, where we start with IID random variables x and look at the sum of xi minus 1 xi. Now, some things are easy to pick off right from there. For example, the expected number of triangles is just going to be the sum of the expected values of these guys here, and that means that this is equal to p cubed. And what we're left with is to count the number of terms here, which of course just means that we have to choose 3 distinct numbers from among the n choices, which is the definition of n choose 3. And so there is the expected number of triangles. And so you can wonder, how should p vary with n in order for this to stay bounded as n grows? Well, n choose 3 is a cubic polynomial, and that means that p cubed had better shrink like 1 over n cubed at least, which means that p, again, like in the Poisson case on the first slide, should be like 1 over n in order for this to stay bounded, but not go to 0. But we'd like to understand more than just the expected value of this random variable. We'd like to ideally understand its distribution. That's going to be a tall order for a fixed n, but maybe we can say something meaningful about the distribution as n grows if pn goes to 0 sufficiently fast. And in fact, we're going to see that in that case, the number of triangles is approximately normally distributed. There's a central limit theorem in this example. In order to see that, we would need to compute the variance of this to start. And in order to at least bound that, we need to look at the dependency graph. Now, to be clear, we started with a random graph GNP, but let's ignore that graph for the moment. Instead, we're just looking at the collection of random variables and looking at its dependency graph, which is not a random graph, it is a deterministic graph. The vertices are just the indices, triangles in other words, triples ijk with I less than j less than k. And we need to know, when are two triangles independent in this random formulation? Well, the terms in the sum that we care about, written like this, are going to be independent if and only if the two triangles don't share an edge. So that means that the dependency graph here has as its vertices all triangles you can draw between any 3 points among a collection of n points. And there's an edge between two triangles if and only if those two triangles share exactly one edge. It would be hard to draw a convincing and understandable picture of what that graph looks like if n is bigger than 4 or 5. But one thing we can do right now is compute the degree of that dependency graph. If I fix any triangle, ijk, I want to look at all of the other triangles that have an edge to it in the dependency graph. In other words, I need to look at all triangles that share one edge with this triangle. But that just means looking at any other vertex that is not in this 3-vertex set. Each one of those can form exactly 3 triangles that share an edge with this one. For example, this vertex here forms a triangle sharing this edge, and this edge. This vertex here forms a triangle sharing this edge, and that edge, and so on. So what that means is that the number of other triangles that share at least one vertex with the given triangle here is just 3 times the number of vertices not in that triangle. That is to say, the degree of each triangle vertex in this graph is 3 times n minus 3. Now that degree does not stay bounded with n, unlike the example that we calculated earlier. However, in the Stein bound that we're going to apply, there's a 1 over sigma squared or sigma cubed in the terms. And so the question will be, does the degree here grow slow enough that 1 over the appropriate power of the variance can dominate it in the Wasserstein estimate of Stein's lemma? So for that, we need to actually calculate the variance of the random variable TNP. Now, calculating the variance is fun, but would take more time than I want to go through right now. And if you're inclined to these kinds of enumerative combinatorics problems, I recommend that you go through the calculation. The answer is the following. And it doesn't matter what we have inside here so much. I just want to note that the variance is actually a quartic polynomial in n. It grows quite fast. And that means that the fact that the degree of the dependency graph grows with n is not going to hurt us here, because we're dividing by something that grows much faster. So we can put all of those things together. We can take the standardization of the number of triangles, and using the Stein bound, if we are very careful, we will be able to show that the Wasserstein distance between that standardized number of triangles and a standard normal is bounded by an absolute constant, which doesn't depend on any of the parameters here, divided by n times p to the 9 halves. And if you'd like to see the details of how all of that plays out, there's an outline in this paper of Ross. So, for example, if we choose our Pn to decay at a rate like 1 over n to the alpha for some positive power alpha, then this shows that if that power alpha is small enough, less than 2/9, then this will go to 0, which means that the number of triangles will satisfy a central limit theorem. Its standardized form will converge in distribution to a standard normal at a polynomial rate. Now, I just want to point out that this is not the optimal result. In fact, Using a more refined asymptotic analysis of these dependency graphs, one can show that you get convergence here if and only if Pn shrinks faster than 1 over n. If Pn shrinks exactly like 1 over n, which is a common regime that is studied, you will not get an asymptotically normal distribution for the number of triangles. If you're interested in these problems, then you may consider going on to a graduate course in probabilistic combinatorics. But I've now shown you that Stein's method can be used to prove central limit theorems even in cases where there is lots of dependence between the random variables. And that's about the best kind of central limit theorem that we know how to prove in general today.